This is my Calculus 1 course. Today we're going to continue to introduce the basic concepts of integral calculus. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. So we discussed in the previous class that for most of this course we've been learning differential calculus, which is finding the slope of a line that's tangent to a graph. And now we're going into integral calculus, where we find the shaded area, the area between the graph of a function and the x-axis. But the problem is area is measured in square units, and it's hard to fit squares in this, against this curved border, because squares have sharp corners. So what we do is we use rectangles to estimate the area under the curve, and we find that as we increase the number of rectangles and calculate the sum of the areas of the rectangles, the sum of the areas of the rectangles approaches a number, and we call that number a limit because the sum cannot go past that number. And whatever that limit is, we say that that is the exact area of this region here. And so in the previous class, we learned how to use Riemann sums to estimate the area under the curve. Today we're actually going to use Riemann sums along with the concept of a limit to find the exact area under a curve. But before we do that, I want to do a little bit more practice with Riemann sums. We're not going to actually calculate the sums. We're just going to practice writing the sums with sigma notation. And these problems are going to be a little bit different. I just want to demonstrate a principle. I want to make sure that you understand function notation before we continue on. So we learned these two formulas. One formula uses left endpoints, the other uses right endpoints. Today we're going to focus on problems where we need to use this formula. When we calculate the exact area under a curve, we use right endpoints, and the only reason that we do that is because the formula that we use to estimate the area with right endpoints, it's a little simpler than the formula that we used for left endpoints. So that's the only reason, really. The formula that we use for right endpoints, you can see that we have an I, but for left endpoints we have to use I minus 1, so it's a little bit more complicated. So we prefer to use this formula. Now, we could change this to I, but then we'd need to change this number, and we'd need to change this, and it would look a little weird. So that's why we prefer this formula here. We're going to estimate using right endpoint. So let's get into the problems today. So again, we're going to review before we actually find the exact area under a curve. Okay, so it says here, write a Riemann sum with sigma notation representing the sum of the areas of the rectangles for each problem below. You do not have to find the value of each sum. So we're not going to actually calculate the sum, we're just going to set it up. So we're practicing sigma notation. So notice that the upper right corners of the rectangles are touching the graph. So again, we're going to focus on right endpoint Riemann sums today. And so I'm going to take this formula and copy it just like we did in the previous class. And I'm going to find the sum of the areas, or I'm not going to find it, I'm just going to write it in sigma notation. So we have 3 rectangles, and remember A is this number, the left bound. so that's going to be 1/2. And B is the right bound, so that's 2. And number of rectangles is 3. And so there we go, we plugged in the numbers. Now we have not actually plugged in the actual function, or we've not used the function. Now remember, this expression represents the height of each rectangle, but this green expression represents the width of each rectangle. That's this here, that's the width. B minus A over N is always the width. Okay, so let's simplify a little bit. So 2 minus 1/2 is 3/2. So we have 3/2 over 3. And then this is a complex fraction. You should know how to do that by now in the math curriculum. That's just going to be 1/2. Again, you take the fraction up here and then you divide by this number here, and you flip the divisor, so that becomes 3/2 times 1/3, which becomes 1/2. So now at this point we're actually ready to get rid of the f and actually determine what we're supposed to use for the function. So what we're going to do is we're going to take this expression here and we're going to rewrite down here. We're going to write the same exact thing. No difference whatsoever. So x squared plus 1 over x. And that's going to be multiplied by 1/2. So f of 1, this whole thing here is what we're writing here. But instead of x, we're going to plug in this. You see that? That's how that works. So this can be very confusing for students. So I'm going to plug in 1/2 plus 1/2 I, and I'm going to square it. Why? Because we're squaring up here, right? Then I'm going to add 1 over the same thing, 1/2 plus 1/2 I. This came from here. Then I'm going to multiply all of that, so I probably could use brackets here. I'm going to multiply all that by 1/2, and that 1/2 came from there. So this whole f of 1/2 plus 1/2 I, that is all of this. And that really confuses students. If you're confused by that, join the club of just about every student out there when they first take calculus. Again, when you're done with this course, you're going to have function notation mastered. So that's it. That's the answer. That's all we're really looking for. We could probably simplify that a little bit, but that's not really the point of these problems. We're just looking for an expression that represents the sum of the areas of those rectangles, and we've got that. Again, the reason that we used this formula is because you can see that the upper right corners of the rectangles are touching the graph. And the only reason we have this part of the graph is it just happens to be, part of that graph, but we didn't really use that. Okay, so let's try another problem. So let me get my formula. I'm going to copy that. And we're going to use the formula for right endpoints again, because you can see, looking at this picture, that the upper right corners of the rectangles are touching the graph. And by the way, I probably should say area estimated area is equal to that. You don't have to do that, but we just want to be clear what we're finding. Okay, so we're using 4 rectangles, and A is the left bound, so that's -5. B is the right bound, that's -1. Actually, four rectangles. And this expression represents the width of each rectangle. Okay, so now we're going to simplify. And so -1 plus 5, that's 4. So we have 4 over 4i. You don't have to show all these steps. You can kind of skip forward. At this point in your math curriculum, it's assumed that you know how to do this basic math. So again, you don't have to show all this stuff. So 4 over 4 is 1. So we have f of -5 plus I, and that's it. All we have to do is convert that. Now we have to go up into our graph and look at our function there. So I'm going to rewrite this. That's the function, that's f. I'm going to rewrite that absolute value of x minus 1/2 x. But I'm going to plug in this where you see an x, everywhere where you see an x. So I'm going to replace that with absolute value of -5 plus I minus 1/2 times -5 plus I. So you see how I plugged in that for every x value? That's what it means. That's what f of -5 plus I means. I know that that's confusing, but that's one of the main objectives of this course. It's not really, I guess I wouldn't say it's one of the main objectives. It's one of the main things that you'll actually do in this course, is you'll learn mastery of function notation. So we want to be clear that all of this is in the sigma notation. So probably should use parentheses, or you can use brackets. And that's it. So that's the answer. Okay, so let's try another one. I'm going to bring down our formula. And the reason we're going to use this same formula is that, as you can see from this picture, the upper right corner of each rectangle is touching the graph. So we're going to use the formula for right endpoints, or the formula using right endpoints. So it just so happens that actually the left corner touches the graph here, but that was just a coincidence. You can see the left corner up here doesn't really touch the graph. So we have 2 rectangles, and A is negative 1/2. B is 2 1/2. Two rectangles again. And then we have B minus A over N, which represents the width of each rectangle. So 2 1/2 plus 1/2 is obviously 3. And so there you go. So now we're ready to use our operations here, which actually define what the function is. So what I'm going to do is I'm going to copy this exact expression down here. It's going to be an exact copy, no difference whatsoever, except wherever there's an x, I'm going to replace the x with this expression inside here. So we have 2x cubed, but instead of x, I'm going to write negative 1/2 plus 3/2 I. And then, so I wrote this first term here. Then we're going to write minus 5 times negative 1/2 plus 3/2 I to the second power, and so on and so forth. Then I'm going to write plus x, but again, instead of x, I'm going to write negative 1/2 plus 3/2 I. And then we have plus 4. So plus x and then plus 4. So that whole thing we just wrote there is this expression here. And then we still have the 3/2 that's multiplied by this. So the blue expression is the height of each rectangle, and the green number is the width of each rectangle. Alright, so that's it. Now when you're writing, I mean, we could simplify this a little bit, possibly. In fact, we could probably simplify it a lot, but that would be a lot of work, and that's not really the point of doing these problems. The point is just to understand how to create this expression. So let's go over this. Whenever you have a lot of calculations, you want to double check and triple check and quadruple check if necessary. So it looks like everything is correct. So at this point, I want you to now try some problems. So I want you to get a picture of this information in problem number 1. Again, we're going to be using the formula for right endpoints today. We're not really going to use the formula for left endpoints. So I want you to try number 4. And I'll leave numbers 2 and 3 in the window for you. So you want to rewrite this equation. It's probably best to show the tool that you're using, not only for the person's sake who's going to read your work, but also for your sake, so you have that right in front of you. So go ahead and try number 4. Notice that the upper right corners of the rectangles are touching the graph, so that tells us that we're going to need right endpoints, so that's why we're using this formula. Okay, so try number 4. When you come back, we'll do it together. Okay, we're back. Okay, so if you got that one right, very good. Okay, so I want you to try number 5. Now notice that again we have the upper right corners of the rectangles touching the graph. So that means we're going to use the formula for the formula that employs right endpoints. So again, that's this same formula. So I'll write that there for you. So try number 5. When you come back, we'll do it together. Okay, we're back. So if you got that answer, excellent. Okay, so I'm going to give you one more chance to take a picture of problem number 1 in this information. And you can take a picture of all this information. And I want you to try problem number 6. Now again, notice that the upper right corners of the rectangles are touching the graph. That means we're going to use the formula for right endpoints. So let me give you that formula. Okay, so go ahead and try number 6, and when you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay, so that was just a little bit more practice converting or writing Riemann sums using sigma notation. So now we're going to find the exact area under a curve. Today so far we've been figuring out ways to find estimates of the area using rectangles. In the previous class, we used rectangles to estimate the area under a curve. Well, we're not going to do that right now. Right now, we're going to find the exact area. But we're going to use the principles that we learned to estimate the area with a Riemann sum, rectangles, in order to help us find the exact area. So let's use this as an example, this graph here. I think we had this graph as an example in the previous class. So let's start by estimating the area with 2 rectangles using a right endpoints Riemann sum. So we're going to use the formula that we just used. That's this formula here, right? So we're going to do the exact same thing that we just did. And so the rectangles are going to look like they're going to look like this. These are going to be the rectangles. Do you agree with that? If we use 2 rectangles and a right Riemann sum, right endpoints Riemann sum. So if you do that, you get this expression, or you get this number down here, 4 3/4. So you can look over this real quick. This is just an example where we're estimating using 2 rectangles. So we plug everything in. We've got our A and B values, and then we change this f of x to this expression here, just like we did in the previous problems. And you can look over that if you want. You don't really need to, because we just did that, so we already got enough practice with that. But now we're actually going to use this expression to calculate. So first, we're going to plug in 1. You see that 1 there? We're going to plug in 1. So you see that pink 1? We plug that in for I. See that? And we calculate that, and we get 3. Then we're going to plug in 2, because that's the next integer up. So we're going to plug in 2. You see the pink 2? Calculate that, and we get 1 3/4. So here's the area of the first rectangle, and here's the area of the second rectangle. Add them up, and you get our estimate. It's not a very good estimate, because we're only using 2 rectangles to estimate this area. We're trying to estimate this shaded area using this rectangle and this rectangle. Okay, so we use this greenish rectangle and this greenish rectangle. We added up the areas and we got, what do we get? We got 4 3/4. So that's what we've been doing so far. But now let's find an estimate for the area using n rectangles. What does that mean? Well, that means we're just going to let n be n. We don't know how many rectangles we're going to use. We could use 2, we could use 5, we could use 80, we could use 1,000,000,000,000 rectangles. But we're just going to let n be n. But we're still going to plug in the numbers that we plugged in before. You see we have, see this 1 here? We're going to plug in 1 for A. And then you see this, these B values, 3, we're just going to plug in 3 for B, just like we did before. We're doing the same thing. No difference whatsoever. Except, instead of letting n be 2, we're just letting n be n, because we don't know how many rectangles we're going to use. Again, we're estimating the area with n rectangles. So we're just letting, we haven't decided how many rectangles we're going to use yet. So this expression here is exactly the same as this expression here. No difference whatsoever. Except instead of 2 for n, we just have n. Instead of deciding how many rectangles we're going to use, we remain undecided about the number of rectangles. Okay, so look this over and make sure you understand. Before we continue, make sure you understand what we're doing. We're doing the same exact thing that we did here. We're just writing n for the number of rectangles rather than 2 or whatever number we choose. We haven't chosen. So then we go down to this step, which is the same as this step here. Everything is the same except we have n rectangles as opposed to 2 rectangles. So this expression at the right looks a little different than the expression at the left. Okay, and then we're going to have to do a lot more math. We can't just start plugging in numbers because we don't know how many rectangles we're going to use. So now, and be careful that you know what's going on here before we continue, because the math is about to get pretty complicated. Now, I want to tell you something really important before we continue here. I want you to listen very carefully. What we're about to do is the difficult way to find the area under a curve, the exact area. We're not going to use this method for 99% of this course. What you're about to see is something that we're not going to use for most of this course. What we're going to do is we're going to find an easier way to do this. Isaac Newton discovered an easier way to do this. But for now, we have to learn the hard way so you can appreciate Isaac Newton's shortcut. Also, it's very important that you know how to do this, because on the advanced placement test, they might give you a problem that's related to this. But what you're about to see is probably the scariest thing in this course. Okay, so I'm not telling you that to scare you. I'm just letting you know that you better be ready for your algebra skills. This is why you had to spend months or years learning algebra, because of what we're about to do right now. So be prepared. This is not going to be pretty. All right? So you've been warned. You're capable of doing this. You're perfectly capable of doing this because you know all this algebra. You've seen it a million times before, but just get ready. Okay, so what we're going to do is we're going to take this expression and we're going to expand by using FOIL. That's 1 plus 2 over ni times 1 plus 2 over ni. We use FOIL and we get to here, right? Now you can stop the video anytime you want to, And you can really get a picture of this with your phone and go through every step. Again, we're finding an estimate for the area using n rectangles, whereas over here we only use 2 rectangles. So I want you to understand what we're doing here. So we use FOIL, and we got this. 2 over ni times 2 over ni is 4 over n squared I squared. That's just basic math. All right? You're just multiplying one fraction times another fraction. And you can put those i's up in the numerator if it helps you. Remember, when you multiply fractions, you just multiply straight across with the numerator, straight across with the denominator. You get 4i squared over n squared. Okay, now notice that we're multiplying negative 1/4 times each of those terms. And by the way, we're going to add these terms. You have the same denominator, so we can add those, and we get 4 over ni. 2 plus 2 is 4. Multiply all those terms by negative 1/4, and we get this expression here. Okay, now we're going to add negative 1/4 and 4, and we get 15 over 4. Just get a common denominator. This is 4 over 1. Multiply, you get 16 over 4, plus negative 1 over 4 is 15 over 4. It is basic mathematics. Okay, so now I'm going to distribute this 2 over n to each one of these terms. And you're probably wondering to yourself, why are we doing this? Let's stop and try to step back here. Why do we have to do this? We have to do this because we don't know how many rectangles we're going to use. We're just coming up with an expression for the estimate of the area using n rectangles. Over here, we just plugged in our I values, and we added the areas, and we got the answer. But here, we don't know how many rectangles we're going to use. So we can't just start plugging in, 1, 2, 3, 4, 5, 6 for I, because we don't know how far we're going to go up when it comes to the number of rectangles. So I'm going to distribute I'm going to distribute 2 over n. So I get, when I multiply these, I get 30 over 4n, right? And 30 over 4n reduces to 15 over 2n, and I distribute the 2n until I get here. You can, again, pause the video, rewind the video, make sure that you understand the basic algebra. And by the way, if you're not understanding everything that we're doing here, we're going to do these problems. We're going to practice these problems, so don't worry about it. So now we're going to use sigma rule number 1 or number 2, however you want to think of that. So remember, we use these sigma rules at the right. A couple classes ago, we learned these sigma rules. If you're adding up the sum of two things, you can group them like so. It's just the sum of A plus the sum of B. So what that means is, if you're adding, for example, if you're adding 2 plus 4, and then you're adding 2 plus 4 again, and then you're adding 2 plus 4 again, well, you can put these 2's together into one sum. That would be like sigma A. And you can put these terms together to make sigma B. That's all that means. You're just regrouping them, basically. So we learned that. So that's what we're doing here. We're taking the sigma and putting it on every term. So now we're using sigma rules 3 and 4. Here we use sigma rule 4, and here we're using sigma rules 3. Now this is where students really start to have some trouble. Let's start with rule number 4. Actually, let's start with rule number 3. That's probably easier to understand. So this tells us that we can take a constant. If a constant is multiplied into every term, this constant c, then you can factor it out of the sum and put it in front of the sigma notation. Believe it or not, this blue expression here and this blue expression here, those are actually constants. Now you're probably going to stop and say, whoa, 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 wait a second. Those are not constants because we have a letter, we have n. But actually they are constants because n is whatever you choose it to be. If you choose n to be a trillion or a billion or 100 or 8 or 17, once you choose what n is, it's a constant. Okay, in this scenario, you can consider the I to be the variable. The I is what's actually changing, but n is just whatever it is once we choose it. So I know that's kind of weird, but that's actually a constant. So notice that we're pulling it out in front. It's multiplied into every term. So it's a constant just multiplied by the function of I, so we can pull it out in front. So that's rule number 3. Again, I know that this is very complicated, but again, this is the part of the course where students really get nervous. But the good news is you're not going to be doing this for the rest of the course. We're going to learn a simple way. And I know what you're going to say. You're going to say, "Well, I don't want to learn this. I just want to go straight to the simple way." Well, you have to know this because again, on the advanced placement test or in any kind of calculus test, they might give you a problem that relates to this. So you need to know your way around this. So over here we're using rule number 4. This, notice that there's no I here. Okay, we have an I here and we have an I here, right? I squared. But there's no I in the first term, so this is just considered to be one big constant. But remember, rule number 4 tells us that if you have a constant, then the sum is just the constant times however many times you're adding it. So let me just show you the logic of that real quick. So let's say that you have sigma, and let's say that this is 5, and let's say that the number in here is 3. What that means is you're adding 3 again and again and again and again, because it's just a number by itself there. That's how mathematicians interpret that. So how many times are you adding 3? Well, 5 times. So 3 times 5 is the sum. That's what this means. Okay. So I know that this stuff is really complicated and it's hard to have to take all this in, but again, this is the part of calculus where things get really intense. So what we're doing is we're just saying, okay, here's our constant. There's no I, so we're just adding this expression how many times? N times. So we take that expression and we multiply it by n. So again, this is the hard way to find the exact area under a curve. So the n's cancel out and you're left with 15 over 2. Now, let's go to some more complex math. All right? Now, again, I know what you're going to say. You're going to say, I don't like this. This is getting too intense. Well, I can't always protect you from messy math. Sometimes the math just gets messy. You have to deal with it. Okay? So we have our special formulas. Remember these formulas that we learned? This is an arithmetic sequence. It's the most basic arithmetic sequence, and using our formula for the sum of an arithmetic sequence, we can come up with this expression. So that's a special expression that you're going to need to memorize for today. So see, we have this sigma here. It's the same thing. That is the same exact expression. You see that? So that's going to turn into n times n plus 1 over 2. Now this expression here, that's what we learned again a couple classes ago. That's that expression. So we have these expressions, and now at this point you might be getting a little weary, and you might be thinking, I've had enough of this, I don't want to continue. But stop for a second and look at this. Look at what we just did. This is an expression that represents an estimate of the area under the curve. Okay, it's an expression that represents an estimate for the area under the curve using Riemann, a Riemann sum, rectangles. It represents an estimate using n rectangles. So if we want to use 10 rectangles, we just plug in 10 for n. If we want to use 1,000,000,000,000 rectangles, we just plug in 1,000,000,000,000 for n. And obviously if we use 1,000,000,000,000 rectangles, we're going to have a better estimate, right? Again, remember what we showed here. The more rectangles you have, the better the estimate of the area. So this is a very, very powerful expression that we just came up with. But let's simplify a little bit. Now, we have an n here, right? That n and one of the n's here, they're going to cancel out. So we're just going to be left with one n in the denominator. These 2's are going to cancel out. And so we're going to be left with this expression. So you can stop the video and go over that if you want to confirm that that's true. You just multiply this fraction and then basically just reduce the fraction, simplify it. Now this n is going to be disappear, and one of these n's down here is going to disappear, so we're going to be left with n squared in the denominator. 2 over 6 reduces to 1 over 3. That's why we just have a 3 down here. And so we're just going to be left with this expression here. Alright, so again, you can stop the video anytime you want to and confirm all this stuff. So this expression, again, represents an estimate of the area of the shaded region that we talked about under the curve in this particular example using n rectangles. This is all based on this example here with this exact function. So we're done. We found an estimate using n rectangles. That's this here. That's the area, or an estimate of the area under the curve, specifically between the x-axis and the graph of the function, using n rectangles. So do you want to estimate the area with 10 rectangles? Plug in 10. 1,000,000,000, plug in trillion, so on and so forth. But now, here's where we reach the whole point of this. Now we're going to calculate the exact area by letting the number of rectangles approach infinity. What that means is n is going to be bigger and bigger and bigger and bigger and bigger. We're going to let the number of rectangles become very, very big. And as the number of rectangles increases, we're going to find that our number, our estimate for the area, is going to approach a number, and that number is what we call a limit. So this expression is going to get closer and closer and closer to a number, but it can't go past that number. That number is the limit, and that number represents the exact area. So what we're going to do is we're going to take this exact expression up here. You see that in blue? We're going to take that exact expression and we're going to copy it down here. But we're going to find the limit of that expression as n approaches infinity, and all that means is that we're going to make n be really, really big. Now, I took this expression here and I went ahead and I expanded it. So I used FOIL to change it to that. You see that? And then I'm going to Well, I guess I could combine these inner terms. You see this? These inner terms here? I guess I forgot to do that. So n plus 2n is 3n. It's not really going to affect the answer, but... Now, we don't need to use this limit rule. Remember we used the limit laws? Technically we're using limit law number 1 or number 2, however you want to consider that. Adding negative numbers is limit law number 1, but if you consider it to be just a difference, it's limit law number 2. But this is what we're using over here. Remember, a limit just goes to each term in this sum, whatever you want to call it. Okay, so the limit goes to each term. We're just considering to be adding negative numbers here. But you don't have to do that. What you can do is you can just look at this expression here and just say, okay, what happens to 15 over 2 as n gets really big? The answer is nothing. You can make n get as big as you want. It's not going to change 15 over 2. That's just going to remain 15 over 2, right? Okay, and what happens to this expression? Now, remember in a couple classes ago, we learned limits at infinity, and we learned that if you have a rational function, and we have two rational functions here, if you have a rational function and the degree of the polynomial in the numerator is equal to the degree of the polynomial in the denominator, so look at these exponents. You see those exponents? They're both the same. If the exponent of the leading term in the numerator and the denominator is the same, then that means that this expression approaches the quotient of the coefficient of the leading term in the numerator and the coefficient of the leading term in the denominator. So 1 divided by 1. So again, this is a rational function. As n approaches infinity, we just get, with this whole expression, just becomes 1 divided by 1. So as n gets bigger and bigger and bigger, this expression just gets closer and closer and closer to 1 divided by 1. Now here we have the same situation. We have the degree of the polynomial in the numerator is equal to the degree of the polynomial in the denominator. So in that situation, this expression, as n gets bigger and bigger and bigger, it just approaches the quotient of these two coefficients of the leading terms. So that just gets closer and closer to 2/3. So if you want to, you can break it up into 3 limits, and that might be easier for you to see. But really, I don't really care if you go straight from here to here. It's pretty obvious that's what's going to happen. Now notice that we have n is approaching infinity. We didn't talk about that when it comes to the limit laws. We didn't say anything about x approaching infinity, right? So do these limit laws work when n is approaching infinity? This is saying x is approaching a, but a is an actual number. Infinity is not a number. So we can't just assume that these laws are going to work for infinity, but it turns out they do. Every limit law except number 8 can be applied when x approaches infinity, but we do have to keep in mind that we're not talking about an actual number. It's infinity. It's not a real number. Now, why doesn't it apply to number 8? Well, you can just look at number 8, and it's kind of common sense why it doesn't apply. But we won't go into that now. That's complicating things. But we have our limit of a constant rule. See that here? If you're finding the limit of a constant, it just equals the constant. So that's that. That's limit law. And I forgot to write that. That's limit law number 6. So we'll write L6. And over here, that's just a basic, that's a limit at infinity. We got those numbers, and then here's another limit at infinity. So we're calculating the value of the limit. and we get these numbers, combine them, and you get 5 and 5/6. So as n gets really, really big, this entire expression approaches this number, 5 and 5/6. It can't go past it. So that's why we use a limit to find the number. It's a limit. The sum of the areas of the rectangles cannot go past this number. It just gets closer and closer to the number. So we say, well, this number must be the area. It's the exact area. So that is the exact area in square units. Remember, area is measured in square units. That's the exact area of this shaded region between the x-axis and the graph of the function. So that's it. That's how you find the exact area under a curve if you're measuring area in square units. Now, notice I wrote square units here. You don't have to write square units, but I just want to make sure you understand that that's actually area measured in square units. Okay, so that's how this process works, and again, that's probably the scariest thing that you'll see in this calculus course. But the good news is we're not really going to use this method for finding the area under a curve. We're going to find an easier method. So don't get all anxious and nervous about this, because this is just a small portion of this course. We're going to use an easier method in later classes. So we learned this expression here for estimating the area under a curve using a certain number of rectangles, right? N rectangles. N might be 5, N might be 1,000, but N is an actual number, right? That we just plug in some number. But if we want to find the exact area, we have to not only do this blue part, we also have to do this purple part here. We have to add that. So when we find the limit as n approaches infinity, that's the exact area. So we have an estimate here, and then when we allow the number of rectangles to get really, really big, we see that there's a number that the estimate approaches for the area under the curve. And whatever that number is, it serves as a limit because we can't go past that number. It just keeps getting closer and closer. So whatever that limit is, that is the exact area under the curve. So this is the master equation that we're going to use for the rest of this class. That gives you the exact. Notice we say exact area under the curve. So a lot of people are pretty proud of this because they consider it to be adding an infinite number of areas. You're adding the areas of an infinite number of rectangles. But that statement doesn't really make sense because there's no such thing as an infinite number, because infinity is not a number. So that's how mathematicians like to think about this, but you can see that it's really not that complicated. All you're doing is allowing this expression, as n gets really big, this expression is approaching a number, and whatever number that's approaching, that's the exact area. It's not really that complicated. So again, this is the height of each rectangle, and this is the width of each rectangle. So I'm going to copy this because we're going to use that. And now we're going to do some problems. So we're going to use this formula for the rest of the class. It says here, use the formula shown previously, this formula here, to find the exact area of the highlighted region in each of the following problems. we're finding the exact area, not an estimate, the exact area. Now, in this problem, we could actually find the area without using this expression, because this is actually just going to be, we just have to find the area of the rectangle, and then find the area of this green triangle, and add them together, and then we get our answer. Alright, in fact, let's go ahead and do that. The area of the blue rectangle, well, that would be width times height, or length, however you want to think about that. So that is 3 times 2, which is 6. And then the area of the triangle, that would be the base is 3, and then the height is 3. And you divide by 2, because remember, area of a triangle is base times height divided by 2, so we get 4.5. If you add those together, we get 10.5. So that is the area we should get when we use this formula. So now we're going to see if we actually get that area. So we'll just leave that work down there so we can verify. Okay, so I'll erase this highlighted stuff here. Let's start plugging in numbers. So we have n rectangles. We're just going to let the number of rectangles be n for now. A is the left bound, that's -2. That's this here, right? B is the right bound, that's 1. So you have 1 minus -2. And again, we're using n rectangles. We don't know how many rectangles we're going to use, so we just say n. Because we're going to let the number of rectangles approach infinity. But for now, we're just saying we have n rectangles. Okay, so we have -2 plus 3 over n, I times 3 over n. So there you go. Okay, but now we need to consider this function here. We're going to rewrite this down here, no difference whatsoever, except wherever you see an x, we're going to plug in -2 plus 3 over n I. Alright, so that blue expression is this up here. Okay, so look that over, make sure you agree with that. Okay, so now we're going to simplify. So we have, we can distribute that negative, and we get that. And feel free to do this math as quickly as you want. I'm showing a lot of steps just because it's beneficial for students to see a lot of steps. But you can, skip a lot of steps if you want. This is just basic math, a lot of this stuff. Okay, so we get down to there, and then we're going to multiply that with that green 3 over n. We're going to multiply that using the distribution property. So then we get 15 over n minus 9 over n squared I. Okay. So now we're going to use our sigma rule. Remember, we have this sigma property here. I'm going to call it, we'll just call it rule number 2 for the sigma notation. So we can distribute that sigma, the sigma symbol, to both of those terms. So there you go, that was sigma rule number 2. Okay, so I want you to be aware of something very important. Notice that we're ignoring this limit right now. I mean, we keep rewriting it, right? Because it's got to be there, but we're not doing anything with it. We're not allowing n to approach infinity. All we're doing is just simplifying this expression. Okay, so now remember, if there's no I here, then all you do is just multiply that expression by however many times you're adding the terms. So that means it's just 15 over n times n. Okay, that is sigma rule number 4. And we're also going to use sigma rule number 3. So if you're baffled by that, again, just look at these rules. We use this rule and we use this rule. Actually, we haven't used this rule yet. We're about to use this rule, number 3. So you can take a picture of that and consult. So rule number 3 is when we pull out this constant here. Now I know, again, that doesn't seem like it's a constant, but it actually is, because we're not allowing n to change right now. We're just assuming that n is going to be a constant number. N is just whatever n is. We're not really changing it. So we pulled that constant out in front. That was rule number 3. So I'm going to copy this because I'm out of room. And again, you can pause the videos as much as you want to pause it to verify all this. So we're almost done. I know that this is a lot to have to take in. So now 15 over n times n, well, that's just 15. The n's just cancel out. And here, well, that is, well, we have a special formula for that. That is n times n plus 1 over 2. Where did we get that? Well, remember, that came from here. That's that special sum that we had to memorize the formula for. So we're getting close. We still have not allowed n to approach infinity. We haven't found the limit yet. We're just finding an expression for n. So now this n and one of these n's, they're going to cancel out. And so maybe I'll just write that. I'm taking it slow here. So now we have 15 minus, and then we're going to distribute. 9 times n plus 1 is 9n plus 9, and 2 times n is 2n. All right. So now the hard part is over. This expression represents an estimate for the area under this curve using n rectangles. N might be a trillion, n might be 1,842. However many rectangles you want to use, you just plug in that number for n. And this is an estimate. The estimate gets better and better the more rectangles you have. The bigger n gets. But if you want to find the exact area, well, we find the limit as n approaches infinity. Now, you can just use this expression if you want to, but if you feel more comfortable using the limit laws, you can break this up into two limits. Alright, whoops, that should be a minus. So now, this is, the limit of a constant is just a constant. Alright, that is limit law number 6, you see that? We learned that quite a while ago in this class. I know it's been a while, but I'm going to say limit law number 6. Now here, we learned this a couple classes ago. This is a rational function, right? And we're finding a limit at infinity. So because the degree of the polynomial in the numerator is 1, and the degree of the polynomial in the denominator is also 1, as n gets really big, this expression just approaches 9 over 2. And it can't go past 9 over 2. So the limit as n approaches infinity is just 9 over 2. Okay, so that's going to be 21 over 2. And if we change that to decimal form, guess what we get? 10.5. That's the exact area in square units. Now remember, we calculated, we got the same number. So we confirm that we did it correctly. So I know that that's a lot of work, but the reason you're required to do this in your first calculus course is that it shows you the process that you would need to use. And to be honest with you, in most cases we can't even use this formula. It doesn't even work for certain functions. But this just gives you a small glimpse into how difficult it would be to find the areas under curves if we didn't have the shorter method, which Isaac Newton discovered back in the 1600s. Okay, so let's try a couple more of these problems before you try one on your own. Okay, so if you're kind of intimidated by this, that's normal. Every student is kind of intimidated by this. That's just what happens in this part of the course. So let's find the exact area, and now we actually need this formula because now we have a curve. We can't use triangles and rectangles. Well, technically we're going to be using rectangles to estimate, but we don't know what the area would be. So the left bound is 1/2. The right bound is 2. And we're using n rectangles. Just let the number of rectangles be n. Okay, and 2 minus 1/2 is 3/2. And again, we're just writing the limit in front there, but we're not really doing anything with that. We're not considering the limit notation right now. And so simplifying that complex fraction, we have 3 over 2n. Okay. So now we're ready to go up to our function here. So we have x squared plus 2. So we have x squared plus 2. And all of that has to be multiplied by 3 over 2n. And you can put brackets if you want. It's debatable whether or not brackets are helpful. They kind of just make the expression look more complicated, but it kind of helps to see that all of that stuff is in the it's in the sigma notation. So this expression here, that is the height of each rectangle in the Riemann sum. And of course, this green expression here is the width of each rectangle. Okay, let's make sure we have that right. Everything looks good. And again, we squared and added 2 because that's what the function tells us to do, right? Okay, so now we just have to simplify this expression a little bit. So we have 1/2 plus 3 over 2ni times 1/2 plus 3 over 2ni plus 2, and all of that is multiplied by 3 over 2n. And then we need brackets. So again, this is all just that blue expression. Okay. Now, if you understand the algebra that we're doing here, you don't have to show so many steps and go so slow. You can do FOIL in your head and just skip right down to, you know, the step down here. You don't have to show all these steps necessarily. So using FOIL, 1/2 times 1/2 is 1/4, and then we get 3 over 4 ni plus 3 over 4 ni. Again, outside terms multiplying, inside terms multiplying. And then the last terms multiply, and we get 9 over 4 n squared I squared. plus 2. And all of that, again, is multiplied by our width. So all of that stuff we just wrote there, again, that's the height of each rectangle. And then multiplying by the green width. Okay, so everything looks right so far. And so now we're going to simplify that blue expression. So we can add the 1/4 and the 2. It looks like we get 9/4. And we can add these terms. We have a common denominator, so we get 6/4n I, because 3 plus 3 is 6. And then again, we're going to multiply by that green width. So again, all that blue stuff became that. And we still have the 3/2n hanging out there. So now we're going to distribute. The green, and we get 27/8n. And we get 18/8n squared. Times I, and we get 27/8n cubed times I squared. Okay. And so now we're going to use sigma property number 1. And separate or create 3 sigma expressions. And probably should use parentheses. Definitely you should use parentheses. So let's double check all this, make sure it's all right. Okay, so I'm going to copy this, because obviously we're out of room. So again, we're finding the exact area. So here we're going to use sigma property number 4, because that's just a constant. So that just equals 27/8n times n. And then here we're going to use sigma property number 3. We're going to pull out the constant out of sigma. That's a number that every term is multiplied by. So I guess we can say we're going to use sigma rule number 3 and 4. Pulling that out. Okay, so there you go. So again, we haven't done anything with the limit yet. So now the ends are going to cancel out, we have 27 over 8. Here we can reduce to 9 over 4n squared. And this here, that's equal to that special formula, remember? N times n plus 1 over 2. And this here, we also have a special formula for that. So recall, we have this formula here. So I'm going to plug that in. So we have n times n plus 1 times 2n plus 1 and that's all over 6. Alright, so now we just have to simplify. So one of these ends cancels out, one of these ends cancels out. And we distribute the 9, so we have 9n plus 9 over 8n, it looks like. Then we have one of these ends cancels out in the denominator, and this end cancels out. Then 27 over 6, that is 9 over 2. 2 times 8 is 16. So we have 9 and 16. And n plus 1 times 2n plus 1. Actually, that should be n squared because we have 2n still down here. And so we're continuing to simplify. So I'm going to use FOIL on that, and we get 2n squared plus 3n plus 1. And then we can distribute the 9, so we get 18 n squared plus 27n plus 9 over 16 n squared. Okay, so now we're ready to consider the limit notation. We're going to allow n to approach infinity. This is an estimate for the area of the shaded region, this area here, using n rectangles. But if we allow n to get really, really big, we see that this expression approaches a number and it can't go past that number. That number is the limit. So again, you don't have to do this, but if you want to, you can separate into 3 different limits, but we know what's going to happen to each of these expressions. So we're using limit law number 1. So what happens to these expressions as n approaches infinity? Well, here we just have a constant, so that is limit law number 6. That's just going to be 27 over 8. And then here we have a rational expression, and notice that the degree of the polynomial in the numerator is equal to the degree of the polynomial in the denominator. And so we learned in a couple classes ago that the limit is just going to be 9 over 8, the quotient of the coefficients of the leading terms. All right. And same thing here. The degree is the same in the numerator and the denominator, so we're just going to end up with 18 over 16. Okay. And we just need to simplify. So we get 9 over 8 here. And if we add all this up, we get, looks like 45 over 8. And you can probably leave the answer that way. It's fine. You can change it to a decimal if you want to, but it's not really necessary. So I knew that that was a lot of work, but again, this is just an intense part of the course. You just have to deal with it. So let's do one more of these problems before you try one on your own. Let's use our formula to find the area of this shaded region. So we're going to do one more of these before you try one on your own. Okay, so we're just going to plug in things for the formula. So A is -3, B is -1. We're using n rectangles for now. And so let's simplify. So now we're going to replace this expression with this expression, except for every x we're going to replace the x with -3 plus 2 over n I. And all that's going to be multiplied by 2 over n. So all that changed into this. And we still have our 2 over n out there. So let's double check, make sure we did this correctly. Okay, so let's continue to simplify. So you can do the foil in your head. You don't have to keep setting it up like I'm doing now. You can just expand that in your head if you want to. So I'm going to need a lot more room. Yeah, I guess I can go ahead and distribute the negative 12. So we get 36 minus 24 over n I, then minus 9, and all that is multiplied by 2 over n. So, continuing to simplify, if we use FOIL, we get the following, and I'm just going to kind of rush through this, add the inner terms. We get negative 6 over ni minus 6 over ni, which is negative 12 over ni. And then multiplying the last, we get 4 over n squared I squared. That's all multiplied by negative 3. So let's double check, make sure we did everything right. Everything looks correct. So 36 minus 9, looks like that's going to be 27. And still all of this is multiplied by 2 over n. And we can use brackets if you want to. Probably best. And whoops, I forgot to write my sigma notation. Okay, so now we're going to distribute this negative 3. So we get negative 27 plus 36 over ni minus 12 over n squared I squared. Alright. And I need another parenthesis there because all of this is multiplied by that green expression. So I want to make it clear that that blue expression became this. This blue expression is the height of each rectangle. And of course the green expression is the width of each rectangle. So it's easy to forget where your parentheses should be, but you really need to use the parentheses correctly. Okay, so notice that these 27s, they cancel out. And 36i over n minus 24i over n is 12i over n. We have minus 12 over n squared I squared. And all that is multiplied by 2 over n. So again, the blue expression is the height of each rectangle. And the green expression is the width of each rectangle, just so you know where that stuff came from. Okay. So just double checking everything. Now we're going to distribute, of course. So then we get 24 over n squared I minus 24 over n cubed I squared. So now we're ready to use our sigma rule number 2, I believe it is. And that tells us that we can separate into two sigma expressions. Okay. So now I'm going to copy this. We're going to use sigma rule number 3 to bring those constants out of the sigma notation. Okay, and as you can see, we have this expression, which we know the formula for, and we have this expression. So we're just going to replace those expressions in terms of, we're going to replace the expression with an expression in terms of n only. So that's n times n plus 1 over 2. And this is n times n plus 1 times 2n plus 1 over 6. We've seen that many times before. And so now we have an estimate for the area that we're looking for, this area here, this shaded area. That's an estimate using n rectangles. And so let's just simplify that expression. And we get, looks like 12n plus 12 over n. And this becomes 4 times 2n squared plus 3n plus 1 over n squared, it looks like. So now let's continue. And now again, you can see what's going to happen to these expressions as n approaches infinity. You don't really have to break it up into, two limits. But if you want to use the limit law number 1, you can do that. That helps us to see that we're finding limits at infinity, like we did in a couple classes ago. Okay, so what happens to this expression? Well, again, the powers are the same in the leading terms. So we learned that as n approaches infinity, this expression just approaches 12 over 1. So I got that from these numbers here. And because the exponents are the same in the leading terms, that expression approaches 8 over 1. Okay, so we're left with 4. So believe it or not, 4 is the exact area that you see here, measured in square units under the curve. Okay, so I know that's a lot of work. I know it's not pleasant, but again, we're not going to be doing this anymore for really most of the rest of the course. So take a picture of this formula. You're going to need that. And you probably should take a picture of all this information also, and all of this information. And I want you to get a picture of number 7. That'll help you. And get a picture of number 8. And get a picture of number 9. And I want you to try number 10. Again, the formula that we're going to use is, let me find that formula, is this formula here. So try number 10. And remember, you're just going to ignore this. You're going to keep rewriting it over and over again, but you're not going to do anything with the limit. You're just plugging things in, and then you're going to use this expression, replace f with that expression, with this plugged into every x value, and proceed from there. But again, you're going to need these formulas here. For this one, you'll need this formula, so you have to have pictures of that. And you also need these formulas, so we need all this information. So try number 10, and when you come back, we'll do it together. Okay, we're back. So the answer is 6. That's the exact area. So if you got that right, excellent. So you can take a picture of this if you'd like to. And I want you to try number 11. So go and attempt number 11. And when you come back, we'll do it together. Okay, we're back. And we can just say 2 1/3, really. That's the answer. So if you got that right, very good. If you made a mistake, that's completely fine. Just go back and figure out what you did wrong and fix the mistake. But you really need to fix the mistake. Don't just pretend that you fixed it. You need to go back and actually fix your expression. Okay, so now I want you to try one more of these problems. This is the last problem for the class. And so I'm going to copy this for you. So there's your formula. When you come back, we'll do it together. Okay, we're back. 13 1/3. So if you got that right, excellent. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1. And screenshot number 2. And number 3. 4. 5. 6. 7. 8. 9. 10. 11. 12. But don't go before you get your homework. Let's look at the homework. Here's screenshot number 1 of the homework. Remember, the homework is not optional. It must be done correctly, completely, and neatly, and kept in order in your binder. Here's screenshot number 2 of the homework. And screenshot number 3. And number 4. And 5. And here are the answers. You must check your answers. If you do a problem and you get it wrong, then you don't just say, well, I'm finished, I can go do something else. No, you have to go back and fix your mistake. The homework must be done correctly. So get that homework done, and I'll look forward to seeing you in the next class.